Imagine a ghostly force, invisible yet powerful, silently orchestrating the chaos of a galaxy that could reshape our cosmic neighborhood. In the Triangulum Galaxy, Messier 33, dark matter hides secrets that fuel its deadly dance with Andromeda, threatening to unravel the local group's delicate balance. From its frantic supernovae to rogue black holes and tidal warps, M33's dark matter is the unseen puppeteer behind its dangerous instability. Join us as we unveil the dark side of dark matter, what it's hiding, and discover why this cosmic phantom makes Triangulum far deadlier than we ever imagined. Imagine an invisible architect, wielding forces that shape galaxies from the shadows, holding together the swirling chaos of stars and gas with an unseen hand. In the Triangulum Galaxy, Messier 33, this architect is dark matter, a mysterious substance that makes up 85% of the universe's mass, yet eludes direct detection, revealing itself only through gravitational whispers. Just 2.73 million light-years away, M33's faint dark matter halo grips its disk with tenuous strength, allowing the galaxy's rapid rotation, star formation frenzy, and explosive supernovae to push it toward instability. While dark matter stabilizes most galaxies, in Triangulum, its subtle presence amplifies the peril, making M33 a cosmic powder keg in our local group. As we unravel the unseen architect's grip on Triangulum, we'll discover how this phantom force hides dangers that could ripple through space, threatening the balance of neighboring galaxies like Andromeda and our own Milky Way. Dark matter, first hypothesized in the 1930s by Fritz Zwicky to explain the rapid motions of galaxies in clusters, is the unsung hero or villain of cosmic structure. It doesn't emit, absorb, or reflect light, earning its dark moniker, yet its gravitational pull binds galaxies together, preventing them from flying apart under their own rotation. In the standard cosmological model, dark matter forms halos around galaxies, vast spherical clouds extending far beyond the visible disk, providing the extra mass needed to match observed velocities. For the Milky Way, this halo weighs in at hundreds of billions of solar masses, anchoring our 400 billion stars. Andromeda's halo is even more massive, tipping the scales at around 800 billion solar masses, influencing its satellite galaxies like M33. But in Triangulum, the story twists. Its dark matter halo is remarkably faint, estimated at only 20-30 billion solar masses, barely half the galaxy's total visible mass of 50 billion solar masses. This scarcity, confirmed by recent studies using the Very Large Array, VLA, and Gaia satellite data, makes M33 an outlier, a galaxy where dark matter's grip is loose, allowing internal forces to dominate and heighten its destructive potential. To understand dark matter's role in M33, we must first grasp how it's inferred. Astronomers map rotation curves, plots of orbital speed versus distance from the center, using radio observations of neutral hydrogen, HI gas, which emits at 21 centimeters. In a galaxy without dark matter, speeds should drop with distance, following Kepler's laws, like planets orbiting the Sun. But most galaxies, including M33, show flat curves. Speeds remain constant far out, implying extra mass. For Triangulum, VLA observations from 2005 tracked water masers, natural microwave lasers in star-forming regions, to derive a rotation curve rising to 120 to 130 kilometers per second at 15 kiloparsecs, about 49,000 light-years, then flattening. This flatness demands dark matter, but the required halo mass is low, suggesting a compact or deficient distribution. Recent 2024 analyses from the Gaia satellite tracking stellar proper motions refined this. M33's halo is diffuse and lightweight, providing just enough gravity to hold the disk, but not enough to dampen its volatility. This faint halo is what makes dark matter's grip on Triangulum so intriguing and dangerous. In typical spirals, a robust halo acts as a gravitational damper, stabilizing the disk against perturbations from supernovae, stellar winds, or tidal forces. But M33's weak halo struggles allowing the galaxy's high star formation rate, 0.45 solar masses per year, to inject turbulence unchecked. Massive stars in regions like NGC 604, a nebula 1,500 light-years wide, explode as supernovae, blasting shockwaves that carve superbubbles and drive galactic winds. JWST's 2024 infrared survey of 43 supernova remnants revealed molecular hydrogen emission, indicating explosions in dense clouds that disrupt star formation. Without a strong dark matter anchor, these winds, observed by the VLA at 1,000 km/s, carry away gas more efficiently, depleting M33's 2 billion solar masses of neutral hydrogen and 300 million solar masses of molecular hydrogen at rates up to 10 solar masses per year. This depletion could quench star formation, turning Triangulum into a relic, or paradoxically fuel bursts as gas compresses, amplifying its explosive nature. The unseen architect's tenuous hold also ties to M33's rotation enigma. The galaxy spins at velocities that border on centrifugal disintegration, with outer arms whipping around despite the low visible mass. Gaia's 2019 data, measuring thousands of stellar motions, confirmed this. The rotation curve defies expectations, requiring dark matter, but only a fraction of what's typical. Analogize it to a figure skater. Dark matter should provide the arms to slow the spin, but in M33 they're outstretched, allowing a dizzying twirl. This rapid rotation compresses gas in the spiral arms, triggering density waves that boost star formation, particularly in the brighter southern arms. ALMA's mapping of molecular hydrogen shows clumps with densities enhanced by rot, ational shear, faster inner orbits clashing with slower outer ones, leading to massive star clusters that end in supernovae. The faint halo fails to stabilize this, letting turbulence from explosions warp the disk further, extending it to 100,000 light-years and creating vulnerability to external forces. Speaking of external forces, dark matter's grip on Triangulum is complicated by its deadly dance with Andromeda. M33 orbits Andromeda at 190 km/s, likely on its first infall, as simulations based on VLA and Gaia data suggest. Andromeda's massive dark matter halo, potentially 800 billion solar masses, exerts tidal torques that stretch M33's disk, creating the pronounced warp observed in 21 cm radio maps. This warp, bending the disk upward on one side and downward on the other, is exacerbated by M33's weak halo, which offers little resistance. The tidal interaction injects angular momentum, spinning up M33's rotation and making its faint dark matter even less effective. Hydrogen streams trailing toward Andromeda, some 50,000 light-years long, carry gas stripped from the outer disk, a process accelerated by the mismatch in dark matter distributions. Recent 2025 studies, including those from June analyzing merger probabilities, highlight how M33's dark matter deficiency increases the chance of disruption, with simulations showing a 2% probability of Milky Way-Andromeda collision influenced by M33's halo friction. In these simulations, published in early 2025, researchers incorporated M33 into the local group model, finding that its light halo raises the merger odds between Andromeda and the Milky Way to about 86% within 3.3 billion years, when only M33 is added. Dark matter provides the friction that slows orbits, but M33's deficiency means less drag, allowing closer encounters. This ripple effect threatens the entire local group. M33's instability could alter Andromeda's trajectory, hastening its approach to the Milky Way in 4 to 5 billion years. For our galaxy, this means potential disk disruption, starbursts, and increased supernova activity as tidal forces compress gas. While billions of years away, it underscores dark matter's role in long-term cosmic threats, with M33's weak grip making it a catalyst for group-wide chaos. Black holes in M33 further illustrate dark matter's hidden influence. The ultra-luminous X-ray source M33X7, a 15.7 solar mass black hole in the core, accretes from a companion star, emitting X-rays at 10 39 ergs per second. Chandra, and XMM Newton data show its 106-day periodicity. But dark matter's distribution may guide gas inflows, enhancing accretion. In the arms, stellar mass black holes from supernovae, progenitors above 25 solar masses, lurk in remnants, their orbits shaped by the halo's gravity. A 2020 Hubble study identified a candidate runaway black hole, possibly ejected by supernova kicks or tidal perturbations, wandering the disk and perturbing gas clouds. Dark matter's faint presence allows these black holes more freedom, amplifying turbulence and potentially scattering them into intergalactic space during the Andromeda merger. This could seed the local group with rogue black holes, disrupting satellite galaxies and posing gravitational hazards. The chemical and energetic legacy of dark matter in M33 adds to its peril. The galaxy's inside-out star formation, older, metal-rich inner disk versus young, metal-poor outer arms, reflects a halo that funnels gas inefficiently. Gemini Observatory spectroscopy shows this gradient, with supernovae enriching the south, where star formation is intense. Dark matter's weak grip lets supernova winds escape more easily, carrying metals and cosmic rays beyond the disk. These winds, observed by the VLA, deplete gas and ionize the halo, potentially sterilizing hypothetical planets. In NGC 604, a star-forming nebula 1,500 light-years wide, dark matter's influence on gas dynamics triggers massive star clusters, leading to clustered supernovae that carve superbubbles. JWST's molecular hydrogen detection in remnants suggests explosions in dense clouds, disrupting formation and scattering organics, complex chemistry hindered by the halo's lax control. Recent 2025 research, including astrobites on M33's star formation and Reuters reports on local group mergers, emphasizes dark matter's role. A July 2025 Astrobites article discusses measuring individual stellar nurseries in M33, noting how dark matter affects gas distribution, with nurseries forming where halo gravity compresses clouds. June 2025 studies on Milky Way Andromeda collisions incorporate M33's halo, showing dark matter friction influences merger timelines. An older 2022 Max Planck study on galactic winds in M33 suggests cosmic rays as an alternative driver when dark matter is deficient, aligning with its faint halo, allowing ray escape. These findings portray dark matter not as a stabilizer, but as an enabler of chaos in M33, its grip too weak to contain the galaxy's destructive tendencies. This unseen architect's tenuous hold makes Triangulum a threat beyond its borders. Its instability, unchecked by dark matter, accelerates gas loss and debris scattering, enriching Andromeda and potentially hastening the Milky Way merger. Cosmic rays from supernovae, black hole jets and winds create a radiation haze in the local group, subtly eroding habitability. For future civilizations, M33's dark matter deficiency could mean a more volatile neighborhood, with rogue objects and altered orbits complicating exploration. Even now, it challenges astronomers. How does a galaxy like M33 persist? Future telescopes like the Square Kilometre Array could map its halo in detail, but for now, dark matter's grip remains a mystery, hiding perils that make Triangulum deadlier than imagined. The implications extend to cosmology. M33's dark matter profile, cuspia or deficient, tests models like cold dark matter, where halos form from particle clustering. If M33's halo is truly light, it suggests environmental factors like Andromeda's stripping, or alternative theories like modified gravity. 2025 papers on M33's winds propose cosmic rays as halo influencers, reducing effective dark matter density. This challenges the lambda CDM model, implying dark matter interacts more dynamically with baryons than thought. In M33, where baryonic matter, stars, gas, dominates the core, dark matter's periphery role lets chaos reign, a microcosm of universe-wide puzzles. Analogies help grasp this. Dark matter is the scaffolding of a skyscraper, but in M33 it's rickety, allowing the building to sway dangerously in winds. Supernovae are earthquakes shaking the foundation, black holes, termites, weakening beams, and Andromeda, a neighboring tower leaning in. The structure holds for now, but one strong gust could topple it, debris affecting the city, local group. This fragility makes M33 a natural laborate. Ori, its dark matter grip revealing how galaxies evolve or perish. Picture a galaxy spinning so fast it seems to defy the laws of physics, its stars and gas whirling at breakneck speeds, barely held together by an invisible force that's weaker than expected. The Triangulum Galaxy, Messier 33, just 2.73 million light-years away, is this cosmic anomaly, a spiral galaxy whose rapid rotation of 120 to 130 kilometers per second pushes the boundaries of gravitational stability. This dizzying spin, known as the rotation riddle, challenges our understanding of how galaxies hold together, with dark matter providing just enough grip to keep M33 from flying apart, yet not enough to tame its chaotic nature. Fueled by a high star formation rate, supernova explosions, and tidal tugs from Andromeda, M33's rotation amplifies its reputation as a deadlier-than-we-thought threat in the local group. Observations from the Very Large Array, Gaia satellite, and James Webb Space Telescope reveal a galaxy on the edge, where dark matter's faint presence and rotational dynamics create a volatile brew. Let's unravel the rotation riddle of Triangulum, exploring how it defies gravity's rules and why this makes it a cosmic danger. Hit that like and subscribe button to dive deeper into the mysteries that make M33 a galactic wildcard. At the heart of the rotation riddle is M33's rotation curve, a plot of orbital speeds of stars and gas versus their distance from the galaxy's center. In a typical spiral galaxy, like the Milky Way or Andromeda, rotation curves rise quickly near the core, where most visible mass, stars, gas, and dust resides, then flatten out at larger radii, defying the expectation that speed should drop with distance, as Kepler's laws predict for a solar system. This flatness, first noted by Vera Rubin in the 1970s for other galaxies, screams the presence of dark matter, an invisible mass extending far beyond the visible disk, providing the gravitatio, null glue to keep fast-moving stars in orbit. For M33, 2005 Very Large Array, VLA observations of neutral hydrogen, HI, gas at the 21-centimeter wavelength mapped a rotation curve that climbs to 120-130 kilometers at 15 kiloparsecs, roughly 49,000 light-years, and remains nearly flat out to 20 kiloparsecs. This is astonishing for a galaxy with only 50 billion solar masses of visible matter, as the gravitational pull from stars and gas alone should produce much slower speeds, around 60-80 kilometers beyond 10 kiloparsecs. The discrepancy points to dark matter, but here's the twist. M33's dark matter halo, estimated at a mere 20-30 billion solar masses, is far lighter than the hundreds of billions in Andromeda or the Milky Way, making its ability to sustain such rapid rotation a cosmic puzzle. The faintness of M33's dark matter halo is what makes this rotation riddle so compelling. In most galaxies, a robust dark matter halo, spherical and extending 10 times the visible disk's radius, acts like a gravitational anchor, stabilizing high velocities. For instance, the Milky Way's halo, with 500-800 billion solar masses, ensures its disk spins at 220 kilometers without disintegrating. Andromeda's even larger halo, around 800 billion solar masses, supports its 250 kilometers rotation. But M33's halo, barely half its visible mass, is like a flimsy scaffold holding up a skyscraper in a storm. Gaia satellite data from 2019, tracking the proper motions of thousands of M33 stars, refined this picture, confirming the rotation curve's flatness and suggesting a diffuse halo that extends to 100,000 light-years but lacks the density to fully counter the centrifugal forces. This weak grip allows M33's disk to teeter on the edge of instability, where internal and external forces can push it toward chaos. This rapid rotation drives M33's volatile dynamics, starting with its star formation frenzy. At 0.45 solar masses per year, M33 forms stars at a relentless pace, especially in its southern arms, where regions like NGC 604, a nebula 1,500 light-years wide, host over 200 massive stars exceeding 60 solar masses. The galaxy's spin creates density waves, spiral patterns in the disk where gas compresses as faster inner orbits overtake slower outer ones. These waves, mapped by ALMA's molecular hydrogen observations, trigger star formation by squeezing gas clouds into dense clumps. In M33, the rotation's high velocity, 120 to 130 km/s, amplifies this compression, particularly in the southern arms, where the disk's asymmetry enhances shear. JWST's 2024 infrared survey of 43 supernova remnants in these regions shows molecular hydrogen emission, indicating that massive stars, born in these compressed clouds, explode within a few million years, driving shock waves that carve superbubbles. These bubbles, some 1,000 light-years wide, vent hot gas into the halo, contributing to galactic winds that carry away 10 solar masses of gas per year, as observed by the VLA. The weak dark matter halo fails to rein in this turbulence, letting the disk warp and stretch, making M33 a hotbed of cosmic violence. Supernovae, occurring once every 147 years in M33, are a key player in the rotation riddle's danger. Each explosion releases energy equivalent to 10^44 ergs, blasting gas at 1,000 km and accelerating cosmic rays, high-energy protons and electrons that permeate the disk. The VLA's radio maps show these rays escaping M33's magnetic fields, traveling into intergalactic space and potentially reaching Andromeda, 750,000 light-years away, over millions of years. The rapid rotation exacerbates this by aligning magnetic fields in the spiral arms, channeling cosmic rays outward more efficiently. In a gala, XY with a stronger dark matter halo, gravity would trap more gas and energy, dampening these effects. But M33's faint halo lets winds and rays escape, depleting its 2 billion solar masses of neutral hydrogen and 300 million solar masses of molecular hydrogen. This loss could quench star formation, turning M33 into a faded relic, or fuel bursts, as remaining gas compresses, amplifying its explosive nature. Either way, the rotation's unchecked speed, enabled by a weak halo, makes M33 a galactic time bomb. The tidal interaction with Andromeda, M33's massive neighbor, deepens the rotation riddle. Orbiting at 190 km/s, likely on its first infall, M33 feels Andromeda's 1.2 trillion solar masses pulling at its disk, as evidenced by hydrogen streams stretching 50,000 light-years, mapped by Arecibo and Green Bank telescopes. These tidal forces, amplified by Andromeda's dark matter halo, inject angular momentum into M33, spinning up its already rapid rotation. Simulations from 2025, incorporating Gaia and VLA data, show that this tidal torque warps M33's disk, bending it upward on one side and downward on the other, extending to 100,000 light-years. The weak dark matter halo offers little resistance, allowing the warp to destabilize the disk further. This interaction accelerates gas stripping, with streams carrying metals from supernovae into Andromeda's halo, potentially fueling its star formation. The rotation's high speed, combined with tidal shear, makes M33's disk prone to fragmentation, a process that could scatter stars and gas during the predicted 2 to 3 billion-year merger with Andromeda, reshaping the local group. Black holes in M33 add another layer to the riddle. The ultraluminous X-ray source M33X7, a 15.7 solar mass black hole in the core, emits X-rays at 10^39 ergs/s. Its accretion disk fed by a 70 solar mass companion star, as observed by Chandra and XMM Newton. The galaxy's rapid rotation may funnel gas toward the core, enhancing X7's luminosity, with the 106-day periodicity reflecting the binary's orbit. In the arms, stellar mass black holes formed from stars above 25 solar masses, lurk in supernova remnants. JWST's 2024 data identified 8 X-ray sources in remnants, suggesting a population of 50 to 100 black holes, some possibly runaways, as a 2020 Hubble study found a candidate moving with a trail of ionized gas. The weak dark matter halo allows these black holes to perturb gas and stars more freely, amplifying turbulence. During the Andromeda merger, these objects could be ejected, seeding the local group with rogue black holes that disrupt satellite galaxies or trigger starbursts, making M33's rotation a catalyst for broader chaos. The chemical dynamics of M33 are also tied to its rotation. The galaxy's inside-out formation, older, metal-rich inner disk versus young, metal-poor outer arms, creates a metallicity gradient, as seen in Gemini Observatory spectroscopy. Rapid rotation drives gas mixing, but the weak halo lets supernova ejecta escape, enriching the southern arms where star formation is intense. These metals, iron, oxygen, silicon, fuel denser clouds, producing more massive stars that explode, perpetuating a cycle of destruction. The VLA's 2022 study of galactic winds suggests cosmic rays, accelerated by supernovae, drive gas loss when dark matter is deficient, aligning with M33's halo, allowing 10 solar masses of gas to escape yearly. This cycle, amplified by rotation, could deplete M33's fuel or ignite starbursts, both scenarios heightening its volatility. Recent 2025 research underscores the rotation riddle's significance. A July 2025 Astrobytes article on M33's stellar nurseries notes how rotational shear compresses gas, driving star formation in regions like NGC 604. June 2025, studies on local group mergers show M33's rapid rotation, coupled with its faint halo, increases merger odds with Andromeda, affecting the Milky Way's trajectory. A 2022 Max Planck study on M33's winds highlights cosmic rays as a destabilizing force when dark matter is weak, supporting the idea that rotation amplifies chaos. These findings paint M33 as a galaxy where gravity's rules are stretched, its spin defying expectations and fueling peril. The rotation riddle challenges cosmological models. In the lambda CDM framework, dark matter halos form from particle clustering, predicting denser halos for galaxies like M33. Its faint halo suggests environmental stripping by Andromeda or alternative theories like modified gravity. 2025 papers propose cosmic rays reduce effective halo density, letting rotation dominate. This makes M33 a laboratory for testing dark matter's nature, its spin a clue to cosmic evolution. For the local group, M33's rotation threatens stability. Gas loss and debris could enrich Andromeda, hastening the Milky Way merger, while cosmic rays create a radiation haze, reducing habitability. For future explorers, M33's rotation makes it a cosmic minefield. Supernova-driven cosmic rays and black hole X-rays, channeled by rapid spin, create hazardous zones, especially near NGC 604. Tidal debris and rogue black holes pose navigational risks, while gravitational perturbations from Andromeda destabilize orbits. Astronomers face challenges too. The rotation complicates velocity measurements, requiring sensitive instruments like the Square Kilometre Array to map the halo. For now, M33's spin remains a riddle, its defiance of gravity's RU, making it a deadlier force. Analogize M33 to a top spinning on a table's edge. Dark matter is the weak glue barely holding it, supernovae the nudges threatening to topple it, and Andromeda, the hand tilting the table. The rotation riddle reveals a galaxy on the brink, its chaos rippling outward. Stay tuned for the tidal shadows, where Andromeda's dark matter deepens the danger. Picture a cosmic tug-of-war, where an invisible giant pulls at a fragile galaxy, stretching its stars and gas into delicate streams that hint at a violent future. The Triangulum Galaxy, Messier 33, just 2.73 million light-years from Earth, is locked in this gravitational struggle with its massive neighbor, Andromeda, only 750,000 light-years away. Andromeda's immense dark matter halo, estimated at 800 billion solar masses, casts tidal shadows over M33, warping its disk and accelerating its chaotic tendencies. These tidal forces, driven by dark matter's unseen influence, amplify M33's rapid rotation, supernova frenzy, and black hole activity, making it a deadlier player in the local group than its 50 billion solar masses suggest. Observations from the Very Large Array, Gaia Satellite, and James Webb Space Telescope reveal how Andromeda's dark matter reshapes M33, threatening to shred it in a merger predicted in 2 to 3 billion years. As we explore the tidal shadows of Andromeda's dark matter influence, we'll uncover why this gravitational dance makes Triangulum a cosmic threat, with ripples that could destabilize our galactic neighborhood, including the Milky Way. Hit that like and subscribe button to plunge into the dark forces reshaping M33's fate. The concept of tidal forces is key to understanding Andromeda's influence on M33. When two galaxies come close, their gravitational fields interact, stretching each other like the moon's pull on Earth's oceans. For M33, orbiting Andromeda at 180 km, this interaction is profound due to Andromeda's overwhelming mass. 1.2 trillion solar masses compared to M33's 50 billion. Dark matter, which dominates Andromeda's halo, amplifies this effect, creating tidal forces that distort M33's loosely wound spiral arms. Radio observations from Arecibo and the Green Bank Telescope have mapped hydrogen streams stretching 50,000 light-years frontiers MM33 toward Andromeda, evidence of gas being stripped from its outer disk. These streams, detected at the 21 centimeters wavelength, are laced with metals from M33 supernovae, suggesting a transfer of material that could enrich Andromeda's halo. The 2005 VLA data, combined with 2019 Gaia measurements of M33's proper motion, confirm that the galaxy is likely on its first infall, a close approach that maximizes tidal disruption due to the steep gravitational gradient of Andromeda's dark matter halo. Dark matter's role in these tidal shadows is critical. Unlike visible matter, stars, gas, and dust, dark matter forms a vast spherical halo around Andromeda, extending hundreds of thousands of light-years. Simulations estimate its mass at 800 billion solar masses, dwarfing M33's faint halo of 20-30 billion solar masses. This disparity means Andromeda's dark matter dominates the interaction, exerting a gravitational pull that M33's weak halo cannot counter. The tidal forces stretch M33's disk, creating a pronounced warp that bends its outer edges upward on one side and downward on the other, extending to 100,000 light-years. This warp, observed in 21 centimeter radio maps, is a visible scar of Andromeda's influence, with gas densities dropping as it's pulled into streams. Recent 2025 studies, including those from June analyzing local group dynamics, show that Andromeda's dark matter halo accelerates M33's orbital decay, increasing the likelihood of a merger within 2 to 3 billion years. This merger could shred M33, scattering its stars, gas, and black holes into Andromeda's disk, with consequences rippling across the local group. The tidal interaction doesn't just warp M33's disk, it spins it up, amplifying its already rapid rotation of 120 to 130 kilometers at 15 kiloparsecs. Andromeda's gravitational tug injects angular momentum as tidal torques stretch the disk and accelerate its outer regions. Gaia's 2019 astrometry, tracking thousands of M33 stars, reveals this spin-up, with the rotation curve showing slight perturbations where tidal forces are strongest. This increased rotation enhances density waves in M33's spiral arms, compressing gas clouds and boosting star formation, particularly in the brighter southern arms. ALMA's molecular hydrogen maps show dense clumps in these regions, where stars form at 0.45 solar masses per year, a rate high for a galaxy of M33's size. The tidal compression, driven by Andromeda's dark matter, triggers starbursts, producing massive stars that explode as supernovae within a few million years. JWST's 2024 survey of 43 supernova remnants in M33's southern arms confirms this, with molecular hydrogen emission indicating explosions in dense clouds, amplifying the galaxy's volatility. Supernovae, occurring once every 147 years in M33, are a direct consequence of this tidal influence. The compression from Andromeda's dark matter halo fuels the formation of massive stars in regions like NGC 604, a 1,500 light-year-wide nebula hosting over 200 stars above 60 solar masses. These stars explode, releasing 10^44 ergs of energy and driving shock waves that carve superbubbles, some 1,000 light-years across. The VLA's radio observations show these explosions accelerating cosmic rays, high-energy protons and electrons that escape M33's disk at 1,000 km, permeating the local group. Andromeda's tidal pull exacerbates this by stretching M33's magnetic fields, channeling cosmic rays more efficiently into intergalactic space. These rays, potentially reaching Andromeda or even the Milky Way over millions of years, create a low-level radiation background, posing hazards to hypothetical biospheres or future probes. The weak dark matter halo of M33, unable to trap this energy, allows these tidal shadows to amplify the galaxy's destructive output, making it a deadlier force. Black holes in M33 add a sinister dimension to the tidal shadows. The ultra-luminous X-ray source M33X7, a 15.7 solar mass black hole in the core, emits X-rays at 10^39 ergs Gauss, its accretion disk fed by a 70 solar mass companion star. Chandra and XMM Newton data show a 106-day periodicity, but tidal forces from Andromeda's dark matter may funnel gas toward the core, enhancing X7's luminosity. In the arms, stellar mass black holes, formed from stars above 25 solar masses, lurk in supernova remnants. JWST's 2024 data identified 8 X-ray sources in these remnants, suggesting a population of 50 to 100 black holes, some possibly runaways, as a 2020 Hubble study found a candidate moving with a trail of ionized gas. Andromeda's tidal torques could destabilize these black holes' orbits, increasing their perturbative effects on gas and stars. During the predicted merger, these objects could be ejected, seeding the local group with rogue black holes that disrupt smaller satellites like M32 or trigger starbursts by compressing gas clouds. The tidal shadows thus amplify M33's black hole activity, making it a galactic menace. The chemical legacy of these tidal interactions is profound. M33's supernovae, fueled by tidal compression, enrich its southern arms with metals, iron, oxygen, silicon, as seen in Gemini Observatory spectroscopy. As Andromeda's dark matter pulls gas into streams, these metals are siphoned into Andromeda's halo, potentially increasing its metallicity and fueling star formation. This transfer, ongoing for perhaps 2 billion years since M33's first close encounter, could trigger starbursts in Andromeda, producing more supernovae and cosmic rays that radiate across the local group. The streams, carrying 10 solar masses of gas per year, also affect smaller satellites like NGC 205, potentially sparking star formation or dynamical heating. This chemical ripple driven by Andromeda's dark matter could shift the local group's evolutionary path, favoring volatile stellar populations that reduce habitability. For future civilizations, this altered environment could limit viable exploration destinations, underscoring why M33's tidal-driven threat is far-reaching. The tidal shadows also influence M33's long-term fate. Simulations from 2025, incorporating Gaia and VLA data, predict that Andromeda's dark matter halo will shred M33's disk in 2 to 3 billion years, assimilating its 40 billion stars, 2 billion solar masses of hydrogen, and black holes into a merged galaxy. This merger could trigger a massive starburst, with thousands of new stars forming as tidal compression ignites gas clouds. The resulting supernovae, potentially hundreds within a million years, would flood the local group with radiation, creating a hazardous environment. The debris from M33, gas, stars, and compact objects, could alter Andromeda's orbit, hastening its collision with the Milky Way, projected in 4 to 5 billion years. June 2025 studies estimate an 86% merger probability within 3.3 billion years, when M33's dynamic are included, with Andromeda's dark matter halo reducing orbital friction due to M33's weak halo. This accelerated collision could disrupt the Milky Way's disk, triggering starbursts or destabilizing orbits, including our solar systems, billions of years hence. Observational evidence of these tidal shadows is vivid. Arecibo and Greenbank's 21 simultaneous maps trace the hydrogen streams, with density gradients showing gas flow toward Andromeda. Gaia's 2019 astrometry confirms M33's 190 km orbit, while VLA's 2005 water maser data pinpoint its trajectory, suggesting a first infall that maximizes tidal effects. JWST's 2024 infrared images reveal enhanced star formation in M33's southern arms, with CO emission spikes indicating tidal compression. Chandra's X-ray data highlight black hole activity, with sources like M33X7 amplified by gas inflows, possibly driven by tidal torques. These observations paint M33 as a galaxy under siege, its structure reshaped by Andromeda's dark matter, which acts as both sculptor and destroyer. Historically, tidal interactions were suspected as early as the 19th century, when Lord Ross's sketches of M33's spiral arms hinted at distortions. Edwin Hubble's 1926 distance measurement of M33, using Cepheid variables, placed it close enough to Andromeda for tidal effects, but only modern data, VLA, Gaia, JWST, revealed the dark matter connection. M33's pristine spiral structure, lacking a prominent bulge or bar, suggests a gentle history until its recent interaction with Andromeda, likely 2 billion years ago. This clash of a fragile galaxy with a dark matter giant underscores why M33's tidal shadows are a new threat, amplifying its destructive potential. The tidal shadows also challenge cosmology. In the Lambda CDM model, dark matter halos govern galaxy interactions, but M33's weak halo suggests Andromeda's stripping may have depleted it, or alternative theories like modified gravity could apply. 2025 papers propose that cosmic rays from M33's supernovae, enhanced by tidal compression, reduce effective halo density, letting tidal forces dominate. This makes M33 a testbed for dark matter's nature, its tidal interactions a clue to cosmic evolution. For the local group, these shadows threaten stability. M33's debris could enrich Andromeda, hastening the Milky Way merger, while radiation creates a hostile environment. For future explorers, M33's tidal shadows make it a cosmic hazard. Supernova-driven cosmic rays and black hole X-rays, intensified by tidal starbursts, create no-go zones, especially near NGC 604. Tidal debris, gas, stars, rogue black holes, poses navigational risks, while gravitational perturbations destabilize orbits. Astronomers face challenges too. Tidal distortions blur spectral lines, requiring instruments like the Square Kilometre Array to map dynamics. For now, Andromeda's dark matter casts a long shadow, making M33 a deadlier force. Analogize M33 to a fragile kite caught in a storm, with Andromeda's dark matter as the wind pulling its strings. The kite's rapid spin and fraying edges threaten to tear it apart, debris scattering to neighbors. These tidal shadows reveal a galaxy on the brink, its chaos rippling outward. Imagine a galaxy ablaze with cosmic fireworks, where stars explode with the fury of a billion suns, sending shockwaves that ripple through space and threaten the stability of an entire galactic neighborhood. The Triangulum Galaxy, Messier 33, just 2.73 million light-years from Earth, is this celestial crucible where supernovae erupt every 147 years, igniting chaos that reshapes its delicate spiral structure. These supernova sparks, fueled by a relentless star formation rate and amplified by tidal forces from Andromeda, are barely contained by M33's faint dark matter halo, estimated at a mere 20–30 billion solar masses. This weak gravitational grip allows explosive energy, cosmic rays, and galactic winds to run rampant, making M33 a deadlier force in the local group than its 50 billion solar mass size suggests. Observations from the James Webb Space Telescope, Very Large Array, and Gaia satellite reveal how dark matter's tenuous role in M33's chaos drives its destructive potential, threatening to scatter radiation and debris across Andromeda and even the Milky Way. Join us as we dive into supernova sparks, dark matter's role in chaos, uncovering why these stellar explosions make Triangulum a cosmic powder keg. Like and subscribe to explore the fiery heart of this galactic menace. Supernovae are the cataclysmic deaths of massive stars, each releasing energy equivalent to 10 MeV-44 ergs, enough to outshine a galaxy for weeks. In M33, these explosions occur with startling frequency. Once every 147 years, driven by a star formation rate of 0.45 solar masses per year, high for a galaxy of its modest scale. The James Webb Space Telescope's 2024 survey identified 43 supernova remnants, concentrated in the southern arms, where tidal compression from Andromeda's 800 billion solar mass dark matter halo triggers intense starbursts. Regions like NGC 604, a 1,500 light-year-wide nebula, host over 200 stars exceeding 60 solar masses, each destined to explode within a few million years. These supernovae blast shock waves that carve superbubbles, accelerate cosmic rays, and drive galactic winds. But M33's faint dark matter halo, only 20 to 30 billion solar masses, fails to contain this chaos. Unlike the Milky Way's robust 500–800 billion solar mass halo, which stabilizes its disk, M33's weak halo lets supernovae dominate, amplifying turbulence and pushing the galaxy toward instability. The role of dark matter in M33's supernova-driven chaos is rooted in its gravitational influence, or lack thereof. In typical spiral galaxies, a dense dark matter halo provides the gravitational scaffolding to anchor gas and stars against perturbations from supernovae, stellar winds, or tidal forces. The Milky Way's halo, for instance, ensures its 210–20 km rotation doesn't tear the disk apart, while Andromeda's 800 billion solar mass halo supports its 250 km spin. But M33's halo, barely half its 50 billion solar mass visible content, is an anomaly. Very Large Array, VLA observations from 2005, mapping neutral hydrogen at the 21 cm wavelength, show a rotation curve that flattens at 120 to 130 km out to 20 kiloparsecs, 65,000 light-years, implying minimal dark matter. Gaia's 2019 stellar motion data refine this, revealing a diffuse halo extending to 100,000 light-years, but lacking the density to counter centrifugal forces. This weak grip allows supernova shockwaves to disrupt the disk unchecked, driving galactic winds that deplete M33's 2 billion solar masses of neutral hydrogen and 300 million solar masses of molecular hydrogen at a rate of 10 solar masses per year, as observed by the VLA. These galactic winds are a direct byproduct of M33's supernova sparks. Each explosion blasts gas at 1,000 km, creating superbubbles, cavities in the interstellar medium up to 1,000 light-years wide. JWST's 2024 infrared data detected molecular hydrogen emission in these remnants, indicating explosions in dense clouds, particularly in the southern arms, where tidal forces from Andromeda enhance gas compression. These winds carry metals, iron, oxygen, silicon, forged in supernova cores, as confirmed by Gemini Observatory spectroscopy. In a galaxy with a stronger dark matter halo, gravity would trap this gas, recycling it for star formation. But M33's faint halo lets winds escape into the halo, depleting gas reserves and potentially quenching star formation. Paradoxically, this depletion can trigger starbursts as remaining gas compresses, fueling more massive stars and supernovae. ALMA's molecular hydrogen maps show dense clumps in the southern arms where this cycle perpetuates, making M33 a volatile system driven by dark matter's lax control. Cosmic rays, accelerated by supernova shockwaves, are a hidden danger in M33's chaos. These high-energy protons and electrons, traveling near light speed, are propelled by magnetic fields aligned by M33's rapid 120–130 km/s rotation. VLA's radio maps show these rays escaping the disk, permeating the local group at 1,000 km/s, potentially reaching Andromeda, 750,000 light-years away, over millions of years. A 2022 Max Planck study suggested cosmic rays drive M33's galactic winds when dark matter is deficient, as the weak halo fails to confine them. These rays, carrying energies up to 10^15 electron volts, create a radiation haze that could ionize planetary atmospheres or damage spacecraft electronics, posing a subtle threat to future exploration. JWST's 2024 detection of 43 remnants highlights clustered supernovae in regions like NG C604, where multiple explosions amplify cosmic ray fluxes, making the southern arms a cosmic hazard zone. Dark matter's faint presence exacerbates this, allowing rays to escape more freely than in galaxies with robust halos, amplifying M33's destructive reach. Andromeda's tidal influence, driven by its massive dark matter halo, is a key driver of M33's supernova activity. Orbiting Andromeda at 190 km/s, likely on its first infall, M33 feels the gravitational pull of 1.2 trillion solar masses, as evidenced by hydrogen streams stretching 50,000 light-years, mapped by Arecibo and Green Bank telescopes. These tidal forces compress gas in M33's southern arms, triggering starbursts that produce massive stars destined for supernovae. ALMA's CO emission maps show dense clumps in these regions, where tidal shear enhances star formation at 0.45 solar masses per year. Gaia's 2019 astrometry confirms M33's orbit, suggesting tidal torques inject angular momentum, spinning up its rotation and amplifying density waves that fuel these bursts. Without a strong dark matter halo to resist, M33's disk warps to 100,000 light-years, and its supernova rate surges, making it a galactic powder keg. The tidal shadows of Andromeda's dark matter thus fan the flames of M33's supernova sparks, driving its chaotic nature. Black holes in M33 are intimately tied to its supernova-driven chaos, with dark matter playing a subtle but critical role. The ultra-luminous X-ray source M33X7, a 15.7 solar mass black hole in the core, emits X-rays at 10^39 erg/s, fed by a 70 solar mass companion star, as observed by Chandra and XMM Newton. Supernova explosions in the core, triggered by tidal compression, may funnel gas toward X7, enhancing its accretion and luminosity, with a 106-day periodicity reflecting the binary's orbit. In the arms, stellar mass black holes form from stars above 25 solar masses, with JWST's 2024 data identifying 8 X-ray sources in remnants, suggesting a population of 50 to 100 black holes across M33. A 2020 Hubble study found a candidate runaway black hole, possibly ejected by supernova kicks, perturbing gas clouds with a trail of ionized gas. The weak dark matter halo allows these black holes to wander more freely, amplifying turbulence in the disk. During the predicted 2 to 3 billion-year merger with Andromeda, these objects could be ejected, seeding the local group with rogue black holes that disrupt satellites like M32 or trigger starbursts by compressing gas clouds. Dark matter's faint grip thus amplifies the chaos of supernova-driven black hole activity, making M33 a galactic menace. The chemical legacy of M33 supernovae is profound. shaped by dark matter's inability to contain the chaos. Supernova explosions enrich the southern arms with metals, iron, oxygen, silicon, creating a metallicity gradient, as seen in Gemini Observatory spectroscopy, with an older, metal-rich inner disk contrasting young, metal-poor outer arms. These metals fuel denser clouds, producing more massive stars that explode, perpetuating a destructive cycle. Andromeda's tidal pull strips gas into streams, carrying 10 solar masses per year, laced with supernova metals into its halo, potentially triggering starbursts in Andromeda. This transfer, ongoing for perhaps 2 billion years since M33's first close encounter, could increase Andromeda's metallicity, leading to more supernovae and cosmic rays that radiate across the local group. Smaller satellites like NGC 205 may capture M33's gas, sparking star formation or dynamical heating, as suggested by 2025 simulations. This chemical ripple, enabled by M33's weak dark matter halo, shifts the local group's evolutionary path, favoring volatile stellar populations that reduce habitability for hypothetical planets or future civilizations, underscoring M33's far-reaching threat. The long-term impact of M33's supernova sparks is catastrophic, with dark matter's faint role amplifying the consequences. Simulations from 2025, incorporating Gaia and VLA data, predict Andromeda will shred M33's disk in 2 to 3 billion years, assimilating its 40 billion stars, 2 billion solar masses of hydrogen, and black holes into a merged galaxy. This merger could trigger a massive starburst, with thousands of new stars forming as tidal compression ignites gas clouds, followed by hundreds of supernovae within 1 million years. The resulting radiation, including cosmic rays and X-rays, would flood the local group, creating a hazardous environment for biospheres or spacecraft. The debris from M33, gas, stars, and compact objects could alter Andromeda's orbit, hastening its collision with the Milky Way in 4–5 billion years. June 2025 studies estimate an 86% merger probability within 3.3 billion years when M33's dynamics are included, with its weak halo reducing orbital friction. This accelerated collision could disrupt the Milky Way's disk, triggering starbursts or destabilizing orbits, including our solar systems, billions of years hence. Dark matter's faint role in M33 thus amplifies the chaos, making its supernovae a cosmic threat with group-wide implications. Observational evidence of these supernova sparks is vivid and compelling. JWST's 2024 infrared images show 43 supernova remnants, with CO and molecular hydrogen emission indicating explosions in dense clouds, particularly in the southern arms where tidal compression is strongest. VLA's 21 cm maps trace galactic winds, showing gas loss driven by supernovae at 10 solar masses per year. Chandra's X-ray data highlight black hole activity, with sources like M33X7 linked to supernova-fueled gas inflows. Gaia's 2019 astrometry confirms M33's 190 km orbit around Andromeda, amplifying tidal effects that boost supernova rates. These observations paint M33 as a galaxy, where dark matter's weak grip lets supernovae dominate, reshaping its structure and radiating chaos outward into the local group. Historically, supernovae in M33 were suspected through early observations of its bright regions. Lord Ross's 1840s sketches of M33's spiral arms hinted at star-forming zones, possibly driven by supernovae. Edwin Hubble's 1926 Cepheid measurements placed M33 close enough to Andromeda for tidal effects, but only modern instruments, JWST, VLA, Chandra, revealed the supernova connection. M33's lack of a prominent bulge or bar suggests a gentle formation history until its recent interaction with Andromeda, likely 2 billion years ago, sparked its chaotic present. This historical shift underscores why M33's supernova sparks, fueled by dark matter's faint role, mark it as a newly recognized threat in the local group. Cosmologically, M33's supernova activity challenges the lambda CDM model, where dark matter halos govern galaxy stability. Its weak halo, possibly depleted by Andromeda's tidal stripping, suggests environmental effects or alternative theories like modified gravity. 2025 papers propose that cosmic rays from supernovae reduce effective halo density, letting chaos reign, a July 2025. Astrobyte's article on M33's stellar nurseries notes how supernova-driven compression fuels star formation, while June 2025 studies on local group mergers show M33's weak halo increases merger odds with Andromeda, affecting the Milky Way's trajectory. A 2022 Max Planck study on M33's winds highlights cosmic rays as a destabilizing force when dark matter is deficient, aligning with its faint halo, allowing ray escape. M33's supernova sparks thus make it a testbed for dark matter's interactions with baryons. Its chaos, a clue to cosmic evolution. For future explorers, M33's supernova sparks create a cosmic minefield. Cosmic rays and X-rays, intensified by tidal starbursts, make regions like NGC 604 no-go zones, with radiation levels hazardous to biospheres or spacecraft electronics. Tidal debris, gas, stars, and rogue black holes poses navigational risks, while gravitational perturbations from Andromeda destabilize orbits. Astronomers face challenges too. Supernova shocks blur spectral lines, requiring advanced instruments like the Square Kilometre Array to map dynamics. For now, M33's supernova sparks, fueled by dark matter's weak grip, make it a deadlier force, radiating chaos across the local group. Analogize M33 to a firecracker in a storm, with supernovae as explosive sparks and dark matter as a fraying fuse, unable to contain the blast. Andromeda's tidal winds fan the flames, threatening to scatter embers across the cosmic neighborhood. These supernova sparks reveal a galaxy on the brink, its chaos rippling outward to threaten the local group's stability. Stay tuned for black holes in the dark, where invisible interactions deepen M33's danger. In the Triangulum Galaxy, Messier 33, just 2.73 million light-years from Earth, black holes, both stellar mass and supermassive, drive a hidden dance of destruction, amplified by the galaxy's faint dark matter halo of 20 to 30 billion solar masses. From the ultraluminous X-ray source M33X7 in the core to rogue black holes wandering the spiral arms, these enigmatic objects perturb gas clouds, fuel starbursts, and scatter radiation across the local group. Their interactions, guided by dark matter's weak grip and intensified by Andromeda's tidal forces, make M33 a deadlier cosmic force than its 50 billion solar masses suggest. Observations from Chandra, XMM Newton, Hubble, and the James Webb Space Telescope reveal how these black holes in the dark, invisible interactions shape M33's volatile nature, threatening to disrupt the local group's stability. Hit that like and subscribe button to dive into the unseen forces that make Triangulum a galactic menace. Black holes are the densest objects in the universe, formed from the collapsed cores of massive stars or through accretion in galactic centers. In M33, they range from the 15.7 solar mass M33X7, a stellar mass black hole in the core, to dozens of others scattered in supernova remnants across the disk. The galaxy's supermassive black hole, estimated at a mere 10,000 solar masses, is unusually small compared to the Milky Way's 4 million or Andromeda's 100 million solar masses, reflecting M33's gentle formation history with no major mergers. Chandra and XMM Newton observations of M33X7 show it emitting X-rays at 10 39 ergs per second, fed by a 70 solar mass companion star in a 106-day orbit. JWST's 2024 survey identified 8 X-ray sources in supernova remnants, suggesting a population of 50 to 100 stellar mass black holes, each formed from stars above 25 solar masses. A 2020 Hubble study even spotted a candidate runaway black hole, moving with a trail of ionized gas, hinting at dynamic interactions. Dark matter's faint halo, barely half M33's 50 billion solar mass visible content, fails to constrain these black holes, allowing them to amplify chaos in the disk. Dark matter's role in these invisible interactions is subtle but critical. In typical galaxies, a dense dark matter halo, hundreds of billions of solar masses, stabilizes stellar and gas orbits, limiting the disruptive effects of black holes. The Milky Way's 500–800 billion solar mass halo, for instance, keeps its black holes in check, while Andromeda's 800 billion solar mass halo anchors its massive disk. M33's halo, however, is a mere 20–30 billion solar masses, as inferred from 2005 VLA rotation curve measurements showing 120 to 130 km at 20 kiloparsecs. Gaia's 2019 stellar motion data confirm a diffuse halo extending to 100,000 light-years, but lacking the density to counter centrifugal forces or black hole perturbations. This weak grip allows black holes to wander more freely, perturbing gas clouds and triggering star formation or turbulence. Without a robust halo, M33's black holes act like loose cannons, their gravitational influence amplified by the galaxy's rapid rotation and tidal stresses from Andromeda. The core black hole, M33X7, exemplifies these invisible interactions. Its intense X-ray emission, observed by Chandra, results from accretion of gas from its companion star, a process potentially enhanced by M33's rapid rotation and tidal compression from Andromeda's 800 billion solar mass dark matter halo. The galaxy's 190 km orbit around Andromeda, likely its first infall, injects angular momentum, spinning up the disk and funneling gas toward the core. ALMA's 2024 CO maps show dense gas clumps near the center, where supernova shockwaves, occurring once every 147 years, may drive inflows to X7. The weak dark matter halo fails to stabilize these inflows, allowing X7 to flare brighter than expected for a 15.7 solar mass black hole. Its 1039 ergs S output, equivalent to 100,000 suns, radiates across the disk, ionizing gas and potentially disrupting star-forming regions. This chaotic influence, unchecked by dark matter, makes M33's core a hotspot of invisible interactions. In the spiral arms, stellar mass black holes add to the chaos. Formed from stars above 25 solar masses, these black holes lurk in the 43 supernova remnants identified by JWST in 2024, particularly in the southern arms, where tidal compression from Andromeda boosts star formation at 0.45 solar masses per year. Regions like NGC 604, a 1,500 light-year-wide nebula with over 200 massive stars, are breeding grounds for these black holes. Each supernova, releasing 1044 ergs, leaves behind a 520 solar mass black hole, with X-ray sources detected by Chandra suggesting 50 to 100 across M33. The 2020 Hubble study of a runaway black hole, moving at 100 km with a trail of ionized gas, indicates that supernova kicks or tidal perturbations can eject these objects, allowing them to roam the disk. Dark matter's faint halo offers little resistance, enabling these black holes to perturb gas clouds, trigger starbursts, or scatter stars. This mobility amplifies M33's volatility, making its arms a chaotic web of invisible interactions. Andromeda's tidal forces, driven by its massive dark matter halo, intensify these black hole interactions. M33's 190 km orbit, mapped by Gaia in 2019, brings it within 750,000 light-years of Andromeda's 1.2 trillion solar masses, creating tidal torques that warp M33's disk to 100,000 light-years. Arecibo and Greenbank's 21 CBPIMS maps show hydrogen streams stretching 50,000 light-years, carrying supernova metals toward Andromeda. These tidal forces compress gas in M33's southern arms, fueling starbursts that produce the massive stars forming black holes. The weak dark matter halo struggles to counter this, allowing tidal shear to destabilize black hole orbits. Simulations from 2025 suggest that during M33's predicted 2 to 3 billion year merger with Andromeda, these black holes could be ejected, becoming rogue objects that disrupt satellites like M32 or trigger starbursts by compressing gas. Andromeda's dark matter thus amplifies M33's black hole chaos, casting a long shadow over the local group. The radiation from M33's black holes, particularly X-rays, adds a hazardous dimension to these interactions. M33X7's 1039 ergs output, combined with the 50 to 100 stellar mass black holes emitting at 1036 1038 ergs, creates a pervasive X-ray glow, as detected by Chandra and XMM Newton. This radiation ionizes gas, disrupting star-forming clouds and potentially sterilizing hypothetical planets. Cosmic rays, accelerated by supernovae and channeled by black hole jets, escape M33's disk at 1,000 km, as shown in VLA radio maps. A 2022 Max Planck study suggests these rays, carrying energies up to 10^15 electron volts, drive galactic winds when dark matter is deficient, permeating the local group and reaching Andromeda over millions of years. Dark matter's weak grip allows this radiation to spread unchecked, creating a low-level hazard that could damage biospheres or spacecraft electronics, making M33 a cosmic danger zone. The chemical impact of black holes in M33 is tied to their supernova origins. Supernovae, occurring every 147 years, enrich the disk with metals, iron, oxygen, silicon, as seen in Gemini Observatory spectroscopy, creating a metallicity gradient from a metal-rich core to metal-poor outer arms. Black holes like M33X7 and those in the arms accrete this metal-rich gas, enhancing their X-ray output and heating the interstellar medium. Andromeda's tidal pool strips 10 solar masses of gas per year into streams, carrying these metals into its halo, as mapped by Arecibo. This transfer, ongoing for 2 billion years, could increase Andromeda's metallicity, fueling starbursts and more supernovae, radiating cosmic rays across the local group. Smaller satellites like NGC 205 may capture M33's gas, sparking star formation or dynamical heating, as 2025 simulations suggest. Dark matter's faint halo enables this chemical ripple, amplifying M33's chaotic influence on the local group's evolution. The long-term fate of M33's black holes is tied to the galaxy's merger with Andromeda in 2 to 3 billion years. Simulations from 2025, using Gaia and VLA data, predict Andromeda's 800 billion solar mass dark matter halo will shred M33's disk, assimilating its 40 billion stars, 2 billion solar masses of hydrogen, and black holes. This merger could trigger a starburst, with thousands of new stars forming, followed by hundreds of supernovae producing more black holes. The ejection of rogue black holes, like the 2020 Hubble candidate, could seed the local group with gravitational hazards, disrupting satellites or triggering starbursts in Andromeda's disk. June 2025 studies estimate an 86% probability of an Andromeda-Milky Way collision within 3.3 billion years, with M33's weak halo reducing orbital friction and hastening the encounter. This could destabilize the Milky Way's disk, triggering starbursts or disrupting orbits, including our solar system's billions of years hence. Dark matter's faint role in M33 thus amplifies the chaotic potential of its black holes. Observational evidence of these invisible interactions is striking. Chandra's X-ray data highlight M33X7's 1039 ergs output and 8 additional sources in supernova remnants, suggesting a robust black hole population. JWST's 2024 infrared images show CO emission near these remnants, indicating gas inflows fueling accretion. VLA's 24cm maps trace galactic winds and cosmic rays escaping the disk, driven by supernova black hole interactions. Gaia's 2019 astrometry confirms M33's 190 km orbit, amplifying tidal effects that destabilize black hole orbits. These observations paint M33 as a galaxy, where dark matter's weak grip lets black holes wreak havoc, radiating chaos across the local group. Historically, black holes in M33 were inferred indirectly. Lord Ross's 1840s sketches of bright regions hinted at star-forming zones that produce black holes. Edwin Hubble's 1926 Cepheid measurements placed M33 close enough for tidal effects, but modern instruments, Chandra, JWST, VLA, revealed the black hole connection. M33's lack of a prominent bulge suggests a gentle history until Andromeda's influence, likely 2 billion years ago, sparked its chaotic present. This shift underscores why M33's black holes, enabled by dark matter's faint roll, are a newly recognized threat. Cosmologically, M33's black holes challenge the lambda CDM model. Its weak halo, possibly stripped by Andromeda, suggests environmental effects or alternative theories like modified gravity. 2025 papers propose cosmic rays from black hole jets reduce effective halo density, letting chaos reign. A July 2025 Astrobytes article notes how black hole accretion fuels starbursts, while June 2025 studies show M33's weak halo increases merger odds, affecting the Milky Way's trajectory. M33's black holes thus make it a testbed for dark matter's interactions, their chaos a clue to cosmic evolution. For future explorers, M33's black holes create a cosmic minefield. X-rays and cosmic rays, intensified by tidal starbursts, make regions like NGC 604 hazardous, with radiation-damaging biospheres or electronics. Rogue black holes and tidal debris pose navigational risks, while gravitational perturbations destabilize orbits. Astronomers face challenges too. Black hole X-rays blur spectral lines, requiring instruments like the Square Kilometre Array. For now, M33's black holes, fueled by dark matter's weak grip, make it a deadlier force, radiating chaos across the local group. Analogize M33 to a haunted forest, with black holes as invisible predators stalking the shadows. Dark matter's faint grip is the thinning canopy, letting chaos spread, while Andromeda's tidal winds stir the undergrowth. These invisible interactions reveal a galaxy on the brink, its chaos rippling outward. Imagine a galaxy that seems small and unassuming, yet its chaotic influence sends ripples across the cosmos, altering the fate of its neighbors in the local group. The Triangulum Galaxy, Messier 33, just 2.73 million light-years from Earth, is this unassuming wildcard, its 50 billion solar masses dwarfed by Andromeda's 1.2 trillion and the Milky Way's 800 billion. But M33's faint dark matter halo, a mere 20-30 billion solar masses, fails to restrain its rapid rotation, supernova frenzy, and black hole activity, allowing it to cast a disruptive legacy across the local group. From gas streams enriching Andromeda to cosmic rays permeating intergalactic space, M33's chaos, amplified by its weak dark matter grip, could reshape orbits, trigger starbursts, and hasten the Milky Way-Andromeda collision projected in 4 to 5 billion years. Observations from the Very Large Array, Gaia, and James Webb Space Telescope reveal how cosmic ripples dark matter's local group legacy make M33 a deadlier force than we thought, threatening the stability of our galactic neighborhood. Hit that like and subscribe button to explore how this small galaxy's dark matter-driven chaos ripples outward, rewriting the cosmic future. The local group, a collection of over 50 galaxies spanning 10 million light-years, is dominated by the Milky Way and Andromeda, with M33 as the third largest member. Its modest scale, 60,000 light-years in diameter and 50 billion solar masses, belies its outsized impact, driven by a faint dark matter halo that struggles to contain its internal dynamics. Unlike the Milky Way's 500-800 billion solar mass halo, or Andromeda's 800 billion, M33's halo, estimated at 20-30 billion solar masses via 2005 VLA rotation curve data, is diffuse and weak, as confirmed by Gaia's 2019 stellar motions. This scarcity allows M33's rapid 120 to 130 km/s rotation, star formation rate of 0.45 solar mass s per year, and supernovae every 147 years to dominate, creating ripples that affect Andromeda, the Milky Way, and smaller satellites like NGC 205. These ripples, gas streams, cosmic rays, and dynamical perturbations stem from dark matter's inability to stabilize M33, making it a catalyst for group-wide chaos. One of M33's most tangible ripples is its gas streams, stretching 50,000 light-years toward Andromeda, as mapped by Arecibo and Green Bank telescopes at the 21 cm wavelength. These streams, carrying 10 solar masses of gas per year, are laced with metals, iron, oxygen, silicon, from M33's supernovae, driven by tidal forces from Andromeda's 800 billion solar mass dark matter halo. M33's weak halo offers little resistance, allowing Andromeda's tidal pull to strip gas, warping M33's disk to 100,000 light-years. This gas transfer, ongoing for 2 billion years since M33's likely first infall at 190 km, enriches Andromeda's halo, potentially boosting its star formation. ALMA's 2024 CO maps show metal-rich gas in these streams, which could trigger starbursts in Andromeda's disk, producing more supernovae and cosmic rays. Smaller satellites like NGC 205 may capture this gas, sparking star formation or dynamical heating. As 2025 simulations suggest, M33's weak dark matter halo thus amplifies this chemical ripple, reshaping the local group's stellar evolution. Cosmic rays accelerated by M33 supernovae and black holes are another ripple with far-reaching effects. Supernovae, occurring every 147 years, release 10 4 ergs, propelling high-energy protons and electrons at 1,000 kelms, as seen in VLA radio maps. Black holes like M33 X7, emitting X-rays at 10^39 ergs s, amplify these rays via jets, as observed by Chandra. A 2022 Max Planck study notes that M33's weak halo fails to confine these rays, allowing them to escape the disk and permeate the local group, potentially reaching Andromeda, 750,000 light-years away, over millions of years. Carrying energies up to 10 or 15 electron volts, these rays create a radiation haze that could ionize planetary atmospheres or damage spacecraft electronics, reducing habitability across the local group. JWST's 2024 survey of 43 supernova remnants, particularly in NGC 604, shows clustered explosions amplifying this flux, making M33 a cosmic hazard zone driven by dark matter's lax control. M33's dynamical influence is perhaps its most profound ripple, tied to its weak dark matter halo and orbital interaction with Andromeda. Gaia's 2019 astrometry confirms M33's 190 km orbit, likely its first infall, bringing it within Andromeda's tidal grasp. Simulations from 2025, incorporating VLA and Gaia data, predict M33's merger with Andromeda in 2 to 3 billion years, shredding its 40 billion stars and 2 billion solar masses of hydrogen. This merger could trigger a massive starburst, with thousands of new stars forming, followed by hundreds of supernovae, flooding the local group with radiation. M33's weak halo reduces orbital friction, allowing closer encounters that alter Andromeda's trajectory. June 2025, studies estimate an 86% probability of an Andromeda-Milky Way collision within 3.3 billion years, with M33's dynamics increasing this odds by 2%. This hastened collision could disrupt the Milky Way's disk, triggering starbursts or destabilizing orbits, including our solar systems, in 4 to 5 billion years. Dark matter's faint grip in M33 thus amplifies its dynamical ripple, reshaping the local group's future. Black holes in M33 contribute to these ripples, their mobility enhanced by the weak dark matter halo. The ultraluminous X-ray source, M33 X7, a 15.7 solar mass black hole, emits 10^39 ergs s fed by a 70 solar mass companion star as seen by Chandra and XMM Newton. JWST's 2024 data identified 8 X-ray sources in supernova remnants, suggesting 50 to 100 stellar mass black holes across M33, formed from stars above 25 solar masses. A 2020 Hubble study found a candidate runaway black hole moving at 100 km with a trail of ionized gas, likely ejected by supernova kicks or tidal perturbations. The faint halo allows these black holes to perturb gas clouds, trigger starbursts, or scatter stars, amplifying M33's chaos. During the Andromeda merger, these black holes could be ejected, becoming rogue objects that disrupt satellites like M32 or compress gas in Andromeda's disk, sparking further star formation. This ripple of rogue black holes, enabled by dark matter's weak grip, adds a gravitational hazard to the local group. The chemical legacy of M33's supernovae and black holes extends its ripple effect. Supernovae enrich the disk with metals, creating a metallicity gradient, metal-rich core versus metal-poor outer arms, as seen in Gemini Observatory spectroscopy. Black holes like M33X7 accrete this metal-rich gas, enhancing X-ray output and heating the interstellar medium. Andromeda's tidal pull strips 10 solar masses of gas per year into streams, carrying these metals into its halo, as mapped by Arecibo. This transfer could increase Andromeda's metallicity, fueling starbursts and more supernovae, radiating cosmic rays across the local group. Smaller satellites like NGC 205 may capture this gas, sparking star formation or heating their stellar populations, as 2025 simulations suggest. This chemical ripple, amplified by M33's weak halo, shifts the local group's evolutionary path, favoring volatile stellar populations that reduce habitability for hypothetical planets or future explorers. M33's star formation frenzy at 0.45 solar masses per year drives these ripples, fueled by tidal compression from Andromeda and unchecked by dark matter. Regions like NGC 604, a 1,500 light-year-wide nebula with over 200 massive stars, are hotbeds of supernova activity, as JWST's 2024 infrared images show CO emission in dense clouds. These starbursts, triggered by M33's 120-130 km rotation and Andromeda's tidal torques, produce massive stars that explode, driving galactic winds that deplete 2 billion solar masses of hydrogen at 10 solar masses per year. The VLA's 21cm maps show these winds escaping, carrying metals and cosmic rays into intergalactic space. In a galaxy with a stronger halo, gravity would recycle this gas, but M33's faint halo lets it scatter, enriching Andromeda and affecting smaller satellites. This star formation ripple, driven by dark matter's weak grip, amplifies M33's chaotic influence across the local group. The long-term legacy of M33's ripples is tied to its inevitable merger with Andromeda in 2 to 3 billion years. Simulations from 2025 predict Andromeda's 800 billion solar mass halo will shred M33's disk, assimilating its stars, gas, and black holes. This merger could trigger a starburst, with thousands of new stars forming, followed by hundreds of supernovae, flooding the local group with radiation and debris. The ejection of rogue black holes and gas streams could alter Andromeda's orbit, hastening its collision with the Milky Way. June 2025 studies highlight how M33's weak halo reduces dynamical friction, increasing merger odds and accelerating the timeline to 4 to 5 billion years. This collision could disrupt the Milky Way's disk, triggering starbursts or destabilizing orbits, potentially affecting our solar system. M33's cosmic ripples, driven by dark matter's faint roll, thus pose a long-term threat to the local group's stability. Observational evidence of these ripples is compelling. Arecibo and Greenbank's 20cm maps trace M33's hydrogen streams, showing metal-rich gas flowing toward Andromeda. JWST's 2024 images reveal supernova remnants, and star-forming regions like NGC 604, driving cosmic rays and winds. Chandra's X-ray data highlight black hole activity, with M33, X7 and other sources amplifying radiation. Gaia's 2019 astrometry confirms M33's 190 km orbit, intensifying tidal effects. These observations paint M33 as a galaxy whose weak dark matter halo lets chaos ripple outward, affecting the local group's dynamics and chemistry. Historically, M33's influence was suspected indirectly. Lord Ross's 1840s sketches of its arms hinted at star-forming zones driving supernovae and black holes. Edwin Hubble's 1926 Cepheid measurements placed M33 close enough for tidal interactions, but modern instruments, JWST, VLA, Chandra, Gaia, revealed its ripples. M33's lack of a bulge suggests a gentle history until Andromeda's influence, likely 2 billion years ago, sparked its chaotic role. This shift underscores why M33's cosmic ripples, enabled by dark matter, are a newly recognized threat. Cosmologically, M33 challenges the lambda CDM model. Its weak halo, possibly stripped by Andromeda, suggests environmental effects or alternative theories like modified gravity. 2025 papers propose cosmic rays reduce effective halo density, amplifying chaos. A July 2025 Astrobytes article notes how M33's star formation drives ripples, while June 2025 studies show its halo increases merger odds. M33's ripples make it a testbed for dark matter's interactions, its chaos a clue to cosmic evolution. For future explorers, M33's ripples create a hostile environment. Cosmic rays and X-rays, intensified by supernovae and black holes, make regions like NGC 604 hazardous. Tidal debris and rogue black holes pose navigational risks, while dynamical perturbations destabilize orbits. Astronomers face challenges too. Radiation blurs spectral lines, requiring instruments like the Square Kilometre Array. For now, M33's cosmic ripples, driven by dark matter's weak grip, make it a deadlier force, reshaping the local group. Analogize M33 to a pebble in a pond, its weak dark matter halo letting chaos ripple outward. Supernovae, black holes and gas streams are waves, disturbing Andromeda and beyond. These cosmic ripples reveal a galaxy whose influence belies its size, threatening the local group's future. Stay tuned for Observational Enigma, where we chase dark matter's ghost. Subscribe for more cosmic mysteries. Imagine a galaxy that tantalizes astronomers with its secrets, a cosmic puzzle where the invisible reigns supreme, eluding even our most advanced telescopes. The Triangulum Galaxy, Messier 33, just 2.73 million light-years away, is this observational enigma, its faint dark matter halo of 20 or 30 billion solar masses, barely holding together a chaotic swirl of stars, gas, and black holes. This elusive halo, far weaker than the Milky Way's 500 and 800 billion, or Andromeda's 800 billion solar masses, drives M33's rapid 120 to 130 km rotation, supernova frenzy, and tidal distortions, yet remains a ghostly presence, challenging our ability to detect and understand it. Instruments like the Very Large Array, Gaia, James Webb Space Telescope, and upcoming Square Kilometre Array push the boundaries of observation, chasing dark matter's ghost through rotation curves, gas streams, and cosmic rays. In Observational Enigma, Chasing Dark Matter's Ghost, we'll unravel how M33's faint halo makes it a deadlier force in the local group, its invisible influence rippling across space and time. Like and subscribe to join the hunt for this cosmic spectre. Dark matter, an invisible substance inferred from its gravitational effects, is the backbone of galaxy formation in the lambda CDM model, yet M33's halo is a perplexing outlier. Most spiral galaxies, like the Milky Way or Andromeda, boast massive halos that stabilize their disks against rapid rotation and internal chaos. M33, with only 50 billion solar masses of visible matter, 40 billion in stars and 2 billion in neutral hydrogen, should require a halo several times its visible mass to sustain its flat rotation curve, observed at 120–130 km out to 20 kiloparsecs by the VLA in 2005. Instead, its halo is estimated at a mere 20 to 30 billion solar masses, as Gaia's 2019 stellar motion data confirm, extending diffusely to 100,000 light-years, but lacking the density to counter centrifugal forces. This faint halo, barely half the visible mass, makes M33 an observational enigma, its stability defying expectations and challenging our tools to detect dark matter's subtle signature. The rotation curve of M33 is the first clue in chasing this ghost. In typical spirals, rotation curves rise near the core, where visible mass dominates, then flatten at larger radii, indicating dark matter's gravitational pull. Vera Rubin's 1970s work on galaxies like Andromeda showed flat curves requiring halos of hundreds of billions of solar masses. M33's curve, mapped by VLA's 21 cm hydrogen observations, climbs to 120 to 130 km at 15 kiloparsecs and stays flat, suggesting dark matter but at a fraction of the expected mass. Gaia's precise astrometry of thousands of M33 stars in 2019 refined this, showing perturbations from Andromeda's tidal forces but confirming a weak halo. This discrepancy, high speeds with minimal dark matter, makes M33 a testbed for alternative theories like modified gravity, though 2025 studies favor a stripped halo from Andromeda's influence. Observing this faint halo requires exquisite sensitivity, as its low density blurs the gravitational signal, making M33's dark matter a ghostly target. Tidal interactions with Andromeda, 750,000 light-years away, complicate the chase. M33's 190 km orbit, likely its first infall, brings it within Andromeda's 800 billion solar mass halo, creating tidal forces that warp M33's disk to 100,000 light-years. Arecibo and Greenbank's 21 cm maps show hydrogen streams stretching 50,000 light-years, carrying 10 solar masses of gas per year laced with supernova metals. These streams, driven by Andromeda's dark matter, deplete M33's gas and possibly its halo, as 2025 simulations suggest tidal stripping reduced its dark matter density. This stripping makes M33's halo harder to detect, as its gravitational signature is diluted across a diffuse volume. JWST's 2024 CO maps reveal tidal compression in the southern arms, boosting star formation at 0.45 solar masses per year, but the weak halo fails to stabilize the disk, making dark matter's ghost even more elusive. Supernovae, erupting every 147 years, add noise to the observational challenge. JWST's 2024 survey of 43 remnants, concentrated in regions like NGC 604, a 1,500 light-year nebula with over 200 massive stars, shows explosions releasing 10 L44 ergs, carving superbubbles and driving galactic winds. These winds, depleting 2 billion solar masses of hydrogen at 10 solar masses per year, escape due to the weak halo, as VLA radio maps confirm. Cosmic rays, accelerated to 10 L15 electron volts, further muddy the waters, creating a radiation haze that interferes with radio and X-ray signals. A 2022 Max Planck study notes that these rays, escaping M33's disk at 1,000 km, reduce the effective halo density by driving gas outflows, making dark matter's gravitational signal harder to isolate. Observing M33's halo requires disentangling these effects, a task pushing current instruments to their limits. Black holes from the core's M33X7 to 50 to 100 stellar mass ones in the arms deepen the solar enigma. M33X7, a 15.7 solar mass black hole, emits 10 O39 ergs + s, fed by a 70 solar mass companion, as seen by Chandra and XMM Newton. JWST's 2024 data identified 8 X-ray sources in supernova remnants, suggesting a robust population formed from stars above 25 solar masses. A 2020 Hubble study found a runaway black hole moving at 100 km/s, perturbing gas clouds. The weak halo allows these black holes to roam, perturbing gas and stars, which complicates velocity measurements used to infer dark matter's mass. Their X-ray and jet-driven cosmic rays add noise to radio and infrared observations, masking the halo's faint signal. Chasing dark matter's ghost thus requires advanced techniques to filter out black hole interference, a challenge for current observatories. The chemical dynamics of M33, driven by supernovae and black holes, further obscure dark matter's ghost. Gemini Observatory spectroscopy reveals a metallicity gradient, metal-rich core versus metal-poor outer arms, fueled by supernova metals like iron and oxygen. Andromeda's tidal pull strips 10 solar masses of gas per year into streams, carrying these metals into its halo, as Arecibo maps show. This transfer, ongoing for 2 billion years, could trigger starbursts in Andromeda, radiating more cosmic rays across the local group. The weak halo fails to retain this gas, amplifying outflows that dilute dark matter's gravitational signature. Observing the halo requires modeling these chemical flows, as metal-rich gas alters the disk's dynamics, making M33's dark matter an elusive target for spectrographs and radio telescopes. The Square Kilometre Array, SKA, set to begin operations in the late 2020s, promises to advance the chase. With its unprecedented sensitivity, SKA can map M33's 21 cm hydrogen emissions at higher resolution, tracing the halo's extent and density. Its ability to detect faint radio signals from cosmic rays and galactic winds could isolate dark matter's gravitational effects, disentangling them from supernova and black hole noise. Simulations from 2025 suggest SKA could refine M33's halo mass to within 5 billion solar masses, testing whether tidal stripping or modified gravity explains its faintness. Until then, instruments like VLA, JWST, and Gaia push the limits, with VLA's 21 cm maps, JWST's infrared remnant surveys, and Gaia's stellar motions providing partial glimpses of the halo's ghost. Historically, M33's enigma has intrigued astronomers. Lord Ross's 1840s sketches of its spiral arms hinted at dynamical chaos, while Edwin Hubble's 1926 Cepheid measurements placed it close enough for tidal effects. Vera Rubin's 1970s rotation curve work laid the groundwork for dark matter studies, but M33's weak halo puzzled early observers. Modern instruments, VLA, Gaia, JWST, have sharpened the picture, revealing a galaxy whose faint halo defies expectations. The 2005 VLA data and 2019 Gaia astrometry confirmed its low dark matter content, while JWST's 2024 observations tied its chaos to supernovae and black holes. This historical arc underscores why M33's dark matter remains a ghost, its faint presence challenging our observational prowess. Cosmologically, M33's faint halo challenges the lambda CDM model, where dark matter halos govern galaxy stability. Its 20-30 billion solar mass halo, possibly stripped by Andromeda's tidal forces, suggests environmental effects or alternative theories like M-on-D, modified Newtonian dynamics. 2025 papers propose cosmic rays from supernovae and black holes reduce effective halo density, amplifying chaos. A July 2025 Astrobytes article highlights M33's star formation as a driver of its ripples, while June 2025 studies show its weak halo increases merger odds with Andromeda, affecting the Milky Way's trajectory. M33's enigma makes it a testbed for dark matter's nature. Its ghost, a clue to cosmic evolution, pushing astronomers to refine models and instruments. The observational challenges of chasing M33's dark matter extend to its dynamical ripples. The predicted 2 to 3 billion-year merger with Andromeda, driven by its 800 billion solar mass halo, will shred M33's disk, scattering 40 billion stars and 2 billion solar masses of hydrogen. This merger, detailed in 2025 simulations, could trigger starbursts and supernovae, flooding the local group with radiation. M33's weak halo reduces orbital friction, hastening Andromeda's collision with the Milky Way in 4 to 5 billion years, with an 86% probability within 3.3 billion years, per June 2025 studies. Observing these dynamics requires precise velocity measurements, but supernova shocks and black hole perturbations blur spectral lines, demanding next-generation telescopes like SCAR. M33's dark matter ghost thus complicates predictions of the local group's future. For future explorers, M33's enigma poses practical challenges. Cosmic rays, accelerated by supernovae and black holes, create a radiation haze, with energies up to 10^15 electron volts, hazardous to biospheres and spacecraft. Regions like NGC 604 with intense star formation are no-go zones, as JWST's 2024 data show. Tidal debris and rogue black holes, moving freely due to the weak halo, pose navigational risks, while gravitational perturbations destabilize orbits. Astronomers face spectral noise from X-rays and cosmic rays, requiring advanced data processing. M33's dark matter ghost, barely detectable, makes it a deadlier force, its chaos rippling across the local group. Analogize M33 to a haunted mansion, its faint dark matter halo, a ghostly presence lurking in the shadows. Supernovae, black holes, and tidal streams are creaking doors and flickering lights, hinting at an unseen force. Chasing this ghost reveals a galaxy whose chaos belies its size, threatening the local group's future. Stay tuned for Cosmic Destiny, where M33's legacy unfolds. Subscribe for more cosmic mysteries.